Hello, I'm Neil O'Hara, and today I'd like to demonstrate my 3D capacitive sensor for you. Before we get started, we all know what a conductor is. It's got two charged metal plates, positive and negative charge on either side, where the area, the dielectric, and the distance between the metal plates are the three main factors, the three only factors in how much conductance the conductor has. This conductance has a very nice property in a circuit we call the RC circuit. A simple resistor and simple capacitor have a charging and discharging curve, as we can see here. And this curve can give us some very nice sensing ability and sensing effect in what we call the capacitive sensor. This image displays a capacitive sensor where any object that interferes with the electric fields, i.e. the electric fields are going to the dielectric, so the new object would be changing the dielectric properties of the capacitor, thus changing the total capacitance. Another type of capacitor sensor is something we simply call the proximity sensor, where instead of two metal plates, we have simply one sensing plate, and then we use the human body, typically the hand, as another edge of the sensing plate. The body, because it's typically grounded with earth, is a neutral charge, so the hand makes a very good negative neutral side of the capacitor. Then with the sensing circuit behind the sensing plate, you can detect through proportionally how strong the capacitor is, and thus how close or far away the hand is. This same principle is used in my 3D capacitor, which I'll pause now and demonstrate. Hello, here is the three-dimensional sensor. Three aluminum plates. As you move your hand around, I believe you can see this. The ball on the screen moves around towards where the hands are on the plate. So go into the deepest corner here, we'll get in that box. So come over here. You start seeing this plate. Obviously it's got a little fuzziness with some of the sensing, but in general speaking it can approximate three-dimensionally where the hand is inside this cube. So we up there at the top. We come back to this farthest corner. You can get that spec again. And we go all the way in. We can get to the farthest corner. Move out. Move back. Move right. Alright. Back to the presentation. To the presentation. Each of the plates is its own RC circuit. Here on the left in this figure, you can see the GPIO pins for each RC circuit. The GPIO pins will drive a plate low and then start measuring to determine how fast the plate charges back up. The charging of the plate is determined by the time constant, which is determined by the capacitance. As the hand approaches the plate, the capacitance increases, the time constant increases, and therefore you can measure how far away the hand is from the plate. Once you linearize and quantize this for all three plates, you can now have a model of where the hand is inside the figure. The charging of the pins is simply a simple digital MOSFET kind of thing, so it has a constant on point for each charging step. The wires are also shielded wires so that it prevents any antenna effects to help this circuit be accurately read. A little bit more detail about the capacitance lines, or the electric field lines of each plate. The charging plate obviously is going to receive electric field lines from the other two plates in the absence of a hand. But when we have a hand here, more and more of the lines will come from the hand, thus changing the capacitance rate of the plate. Now, obviously the closer the hand is to the plate, the more capacitance it is, and that's how you measure where it is inside the box. Here are some example values. The lower right corner in blue is the farthest out distance from the box, lowest values, and the upper left or the red values are the deepest corner of the box where it's closest to all three plates. Just to give an example of the proportional sampled time constants here. And this is how the 3D sensor works. And thank you.